Welcome everybody. It's a wonderful pleasure for me to see so many of you coming here to our summer school from all over, not Germany, not only Europe, but from all over the world. So my name is Frank Neese and I will say a few introductory sentences for you before we start with the real school. And let's see, first things first is please be so kind to turn your cell phones off, and then we all have a very peaceful experience here in Neese. So before I start talking about the school and what we're going to do and what you will hear, I want to give credit to the people who did the bulk of the organization. And so you see I'm listed here, but I did next to nothing, and all of the other people here on the slide, they did really the bulk of the work. That is Serena, Dimitrios, and Dan for the scientific part of it, and Esther Schlammann and Marie-Andrés for much of the logistics. So if you have any question on when you have to be where and how and why, and please ask these people. They know what they're doing, and they have carefully taken care of everything. So it's a great pleasure for me then. So I went back memory lane, and I figured, oops, that is all. That was too fast. And modern technology is too fast. So we are already 16 years old. So in 2 years we're legal here. So we started this in 2009. We're still at the University of Bonn, and it has a certain background because we figured the kind of thing that we're interested in doing is to combine computational chemistry and molecular spectroscopy on transition metals and open shell systems. That was something that is barely taught in universities, and so we figured there is a need to teach that, especially to people at the graduate level. Then it's now you're in your PhDs or in your postdocs, and you try to solve first world problems, and then you don't have time to spend years and years like reading this book and that book, and there isn't really a single source where all of this is documented. So we were poised to write a book. We kind of did write a book. We never finished that book, but eventually I think it will come out. And so far you have motivation to come to us and do the school together with us. Yeah, so we started in Essen in 2009 and 2013. Then we went to Gelsenkirchen. However, the charm of Gelsenkirchen was not, I would say, universally appreciated, and despite its undeniable charm. And so that's why we decided from last year on that we're going to do this here on campus, and that also has the additional benefit that we can do a real hands-on practical course where you can actually see the labs and see the instruments and get like first-hand information on like how these experiments that we're that we're going to talk about will work. I also should give credit to our friend and mentor Eckhard Bill. He was very instrumental in not only setting up the school, but also setting the stage for much of what you're going to hear. I think he has been a mentor to both Serena and me, and also to Dan, and so he has been a really wonderful friend to have, and like the best spectroscopist I've ever known in my life. And so everything I learned about spectroscopy I learned from Eckhard, and he tragically passed away a few years ago, but the school is also to honor his legacy and his memory, and he had really profound impact on everything that you're going to hear here. So with that, like, this thing is really not working. Let me talk a little bit to you what the mission of the school is, and so what we are doing here that you may not be able to hear anywhere else. And so I think what brings us here together is transition metals. And transition metals are fascinating. They're everywhere in nature, and they're everywhere in biochemistry, they're everywhere in chemistry, they're everywhere in physics. And they have these peculiar properties. And part of it is that transition metals are beautifully talkative to us in terms of having these very rich spectroscopic properties. They have beautiful optical spectra, beautiful colors everywhere, beautiful magnetic properties, and with it there comes a certain complexity in the electronic structure. So when you learn computational chemistry on organic molecules, you often get relatively simple, like carved in stone recipes. If you want to calculate this, you like do A, B, C, D, bang, 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 and you get a number and you can trust the number, and that's it. And that's not how either theoretical or experimental transition metal chemistry works. And so I think it's very important to us that you breathe in some of the culture of the electronic structures of transition metals and understand the connection to the physical properties that they have, because ultimately that will also teach you about the reactivity of these compounds. And so it's not that you leave things to miracles, right? Like there's a lot of mystique and miracles that surround the properties and the electronic structures of transition metals, and part of what we want to do here is to take away the mystery. Then is, for example, many computational chemists, when you say the word transition metals, they default to multi-reference. Wrong. Completely wrong. Then it couldn't be more wrong. And in order to demystify that, that's part of what we want to do here. So let's take a brief look in where the complexity is coming from. And the complexity is coming from the fact that the d orbitals, or then when we go into the f block, have orbitals that are kind of semi-weakly interacting with the surrounding ligands. And the consequence of that is that these orbitals are relatively closed spaced. And then when you start filling in electrons, they can do all kinds of crazy things, because there's a multitude of spin state that arises. And so now I really give up here. Then is so and there also is significant covalency in these bonds. And then you may have unpaired electrons, and these unpaired electrons, each electron has a spin, and these spins can couple to a given total spin, and they can couple to a given total spin in many different ways, and that creates a very interesting and complicated manifold of electronic states. And to probe these electronic states with spectroscopy, that is what we has a certain systematics, and this is the systematics that we want to teach you, right? Due to the fact that these orbitals are relatively close spaced, you often also have quite a dense manifold of low-lying excited states, and not only singly excited states, but also doubly excited states, or like spin flip excited states, so like states where many of you are used to when you talk about optical spectra. You say, that's this orbital to that orbital, and that doesn't work anymore for open shell transition metal complexes. And we will go into much more detail of that in the lectures on optical spectroscopy. But it's part of why this transition metal chemistry is so complicated computationally. Then is right. So it's a complex coupling of the unpaired electrons and the rich multiplet structure. And then, of course, you have the whole big field of magnetically interacting transition metal ions, where open shell species start to interact, and that creates this whole like different world of magnetism and magnetic properties. And we're also will teach you at least like the most important things. Then transition metals start to be heavy, so you have to have relativistic effects once you treat that, in particularly the spin orbit coupling, and I'm sure that Dimitrios will in his lecture talk about it. And then you may also have the situations where you have electronic degenerate states or nearly degenerate states, and that creates crazy magnetism where you get all kinds of nonlinear response to, say, external magnetic fields. And all of this creates like a very, very highly challenging and highly complicated electron dance, right? And this electron dance, the rules of this electron dance, that is what we want to teach you here. And so let me emphasize that what we don't want to do, and what we don't want to do is like traditional orthodox computational chemistry. And so when you open a chemistry journal, you very often, like you're almost impossible to not find a paper that has a figure like this, right? Where you have a chemical reaction and you have the reactants and the products, and then you have and then you have like intermediates and transition states, and then you have like kcal, 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 up, down, up, down, up, down, up, down, and then you get one of these terrible acronyms here that quantum chemists are so guilty of. Then I'm always saying that quantum chemistry is only the second worst discipline of science, and it's like I think genetics is by far worst, and like, but we're a solid second in terms of polluting the air with cryptic acronyms. Yeah, but the important thing is the following, and if you only take this from the entire school, then I'm already happy. Then nothing is a certain way because somebody did this or that calculation, right? So when you read a paper that says in the abstract already the mechanism was proven by DFT to be this or that, that's complete garbage, right? That is not true. It's just bad science, then is, yeah, because it's not even science, then is, right? So a calculation by itself in isolation proves nothing, then is, right? It's a working hypothesis that is to be tested against experiment, and if you don't test it, then it will remain a working hypothesis. A good one very often, and you can use calculations to wonderful advantage to guide your thinking, to train your intuition, to fill in blanks where the experiment can't be done, etc. But it's very important to me that like you internalize the mindset that the calculation isn't proof of anything. It's just like a very potent aid that helps your chemical thinking, and if you use it this way, then you make the best the best out of it. So let me emphasize it some further. So if we have a chemical reaction that has reactants and products, somewhere the chemical magic that you often want to understand are the intermediates, and then you want to know the structure of the intermediates. And it is very clear that you can't do crystallography on these intermediates, at least most of the time. You can't do NMR in most cases of these intermediates, so you don't know the structure, and all you get is perhaps just a spectrum. And it's easy to see that a spectrum like this, like a Mössbauer spectrum in this case, has 6 peaks, and you can't possibly deduce 3n minus 6 degrees of freedom, meaning the geometric structure of these intermediates, from the spectrum alone, right? But what you can do is to ask a more modest question, and the more modest question is which structures are compatible with the observation, right? And that is where we want to get at. So because most of the time you have a pretty good idea from all the analytic chemistry where you start and where you end, and that means there is a finite number of possibilities how these intermediates could look like. And then it's up to you to like use your chemical imagination to propose structures for these intermediates. And then if you have an algorithm to calculate the spectroscopic property that you have observed here, then you can compare that to reality, and then you can rule out the structure in case it disagrees with the experiment to more than the known error bar of the calculation. Okay, so it's never a positive proof, it's a falsification, right? So, and that means also in reverse, the more spectroscopic properties you can lay your hand on, the better your falsification process will be. If the calculated property agrees with the experiment, that's not a positive proof that the structure is correct, because there might be many structures that have similar spectra. But every spectroscopic method is sensitive to a different detail of the geometric and the electronic structure. Some are very reactive to protons, and some are very sensitive to bond distances, etc., right? And so the picture gets the better the more spectroscopic properties you can lay your hand on. Yeah. So of all the things that you can connect to in terms of connecting experimentally chemistry and experiment and theory, there is the thermodynamics, and the thermodynamics is of course the overall energetic landscape in which the chemistry is happening. It's of very obvious importance, but it does not involve the catalyst. The overall thermodynamics does not even involve the catalyst, right? So it's just the overall rate of change of the free energy throughout the reaction. Right? And why it's important, you don't learn mechanism from thermodynamics, and in addition, there's the fact that there isn't very much data available. Then there is the kinetics, the reaction rates, and so if people went through the enormous pain of measuring that, then that's, and disentangling that, which may take years, then that's a great set of data to connect to. But what is abundantly available is spectroscopic information. Libraries full of spectra of reaction intermediates and all kinds of things that have been observed. And so that is that enormous treasure of experimental data that we as theoreticians can connect to and can use for the purpose of falsification, right? And like spectroscopy is the experimental way to study electronic structure. That is the important thing, right? And that's why, in my opinion, has been lifelong my opinion that spectroscopy is the absolute best meeting ground between theory and experiment, right? And that is the mindset that we want to convey to you here, right? And so that also has some bearings on like the philosophy of science, and I know that worldwide, nobody is ever hearing lectures on the philosophy of science. That is, which I find a real pity, because it is so overwhelmingly important, like with which mindset you even start your studies, that I think it would be worthwhile for anyone to really hear about it, at least in its essence. And so what we're talking about here is essentially what Popper told us about the philosophy of science, because he said, I shall certainly admit a system as empirical or scientific only if it's capable of being tested by experience. Right? And these considerations suggest that not verifiability but falsifiability is a system is to be taken as a criterion of demarcation. That means, Popper says that, like, if you make a scientific statement and it cannot be tested experimentally, it's not science. Right? And so when you just like run your B3-Lib calculation through the computer, your reaction mechanism, and you're not testing it experimentally, then it's not even science. That's a very extreme point of view, and not one I 100% agree with, but I only 98% agree with. And I think it needs a supplement. And for that supplement, I want to quote Max Planck here, our name giver, and he said, experiments are the only source of knowledge at our disposal, and the rest is just poetry and imagination. And I don't think he meant it in a dismissive way. I mean, I'm putting words in his mouth now, so I don't exactly know what he meant, but the way I'm reading this statement is the following: that of all the things that we can, say, calculate, I personally make a very clear and sharp distinction in my mind between observables and interpretation aids, right? And the observables, these are the things you can measure, right? Like dissociation energies and dipole moments and chemical shifts and molecular masses and excitation energies, etc. And they have unambiguous values that within the error bar of the experiment must be reproducible and correct, right? If the experimentalists did their job properly, yeah? And so either your calculation agrees with that or it doesn't, period, full stop, right? So you can always tell a bad calculation from a good calculation, because when you judge on the basis of the observables, right? And the total energy in principle is an observable, in practice it's not. But then we come to the second part, yeah? So Popper is here, yeah? And the second part is the interpretation aid. And the interpretation aid, these are soft concepts that are not unambiguously defined. Things like resonance, hybridization, orbitals, ligand fields, partial charges, bond orders, pi systems. So none of that has a rigorous definition in quantum mechanics, right? So quantum mechanics doesn't know any of that. Then is so, but I deeply believe, as chemists, we cannot live without this, right? We cannot talk chemistry to each other without recourse to these concepts, right? And that's why it's very important to have them, because these are models that create a language, and in that language we can communicate, because otherwise we could only communicate between, I don't know, about printout of numbers from a computer, and that would be really hell of boring then, is right. And so these interpretation aids, they're important. I think they're central to the culture of chemistry, even if they're not rigorously quantum mechanically defined, right? So, but it also means it's to some extent a very personal thing by which of these interpretation aids or concepts you are inspired, right? And I'm not telling you by what you have to be inspired. I can tell you what inspires me, but that is really very different, right? For example, there is the atoms and molecule theory that I couldn't care less about, but like there is like, say, the NBO analysis that I find quite useful. If it's the way around for you, perfect, no problem, right? And so that's why I think if you want to pick a fight over the observables, but don't fight over the interpretation aid, and let people be inspired by what they're inspired by. There even is a famous concept in theoretical chemistry that is the so-called Pauling point. And the Pauling point is reached when you get a perfect answer from a very simplified model, and that simplified model is completely wrong, then is right. But that is the Pauling point. That is, but yet, for example, I mean, can you imagine like talking about aromatic systems without the concept of what a pi system is and Huckel theory and all that? I cannot, right? And that's why it's important to do this time. So when you kind of implement this way of thinking, then you realize that there is the geometric and the electronic structure of the compound, and they're intimately linked to each other, of course. And the electronic structure is then reflected in the spectroscopic properties of these compounds. And on the other hand, the electronic structure is also then linked to the reactivity. So you can basically use computation like to close that circle between geometric structure, electronic structure, physical properties, and reactivity, right? Because that is what you're seeing in the spectra. And like once you're educated, you can really read the electronic structure of the spectra that you observe. So I want to so that is basically the mindset that we're having when we created that school. And in order to implement that, you need the tools. And so we will teach you the rules of like how to press the buttons, and like how your input files have to look like, and how the spectrometers work and everything. But it's important to keep the mindset in mind. So I wanted to say a few words about the tool that we will be using here at the school, which is the ORCA quantum chemistry program. And if you use a different or prefer a different computational chemistry program, that's totally fine, right? Then that is not this is not here an advertisement exercise, but it is something. It's something that you choose a tool that you feel most comfortable with. I just wanted to show you, like, spend a few minutes talking about where it's coming from, and this is what it feels like the medievals. That is when I started this during my PhD, like a couple of 100 years ago. And I was given the task to compare two enzymes here, and that one was cytochrome C oxidase and the other was nitrous oxide reductase, and they had one thing in common. And that one thing in common was they had an EPR spectrum that was really, really unusual, and it was clear that it came from a copper side. And my PhD advisor, a really nice guy, like Peter Kronek, he asked me, like, okay, what's the structure then? So what is that common structure that is in both of these enzymes that gives rise to that spectrum? And my immediate reaction to that was this, and I don't know. And how could I know? But it became very clear that the answer must come from quantum mechanics, right? And so you must be able to like calculate spectroscopic properties on the basis of quantum mechanics. And at that time, like even a Hartree-Fock calculation on benzene was an adventure, then is right. So basically wasn't going to happen. So it had to be very simplified quantum chemistry, and that's what I did, I studied that, and I wrote a very early version of the ORCA program, actually in the beautiful language of Turbo Pascal. Then is yeah, that is yeah. I know none of you knows that what that is, but we succeeded. And we're able to really calculate the EPR spectrum here. That MCD spectrum was probably the first MCD spectrum really calculated by quantum mechanics, the absorption spectrum. And what it showed was that copper center was then a mixed valence dicopper center, a dimer. And that was also had the first metal-metal bond that was ever seen in biology. That's a detail. So we had lots of fun in with that old program, and then like lab mates started to use it, went on as postdoc, but it was the late 90s, so I've been lying, it was not the medievals in this, but but it just fell out of favor. It was semi-empirical quantum chemistry, and like it was clear it wasn't going to be accepted much longer because everything had to be DFT, and so that was a bummer. And then that basically triggered then the first actual ORCA version. So the one that is still the basis of what you're going to use now in your practical, and that was in 1999. And now, 25 years later, it became a very, very big thing. Like it's typically being worked on by about 20 or so developers here in Mülheim, and then our collaborators around the world, and then also the employees of the company Facts that I'm going to tell you about in a second. So we're now at ORCA 6.1, and so we were very engaged, and it was important to us that we release it before the school so that you can work with us. So in June this year, ORCA 6.1 was released, and that is what you're going to use. So just a brief few lines. So it started in 1999, mostly developed in Mülheim. And just to give you an idea about like how big that project is, so I've counted the number of source code files lately, and there were 55,000 different files with source code, right? And so this is millions and millions of lines of code. So today it's the second most used quantum chemistry program in the world. As of this morning, there are 91,000 registered academic users, and a few thousand more that have registered over other sources and supercomputer centers, etc. And then together with the commercial users, I think it's roughly over 100,000 users. So we made one commitment, and that we will stand by and have contractually guaranteed that ORCA will always be free for academics. And yeah, so you will always get your hands on it for free, and commercially it's sold by the company Facts. And I think it's pretty much a state-of-the-art program, and not only in terms of its feature set, but also in terms of its performance. And that was also the reason why a couple of years back the company was founded. Facts is selling ORCA to industry very, very successfully. So they grow so fast that like at least once a year they have to change into new offices. So basically all of big chem industry has signed on to ORCA. All major computer manufacturers, because quantum chemistry is one of the best stress tests for computer hardware, and yeah, indeed, yeah, indeed, and so that's why all of the major computer manufacturers signed on to it, and now also major social media companies. I have absolutely no idea what they do with quantum chemistry, but that's none of my business, right? So the users. User number is still going somewhere between quadratically and exponential, and this is a comparison to citation statistics, that is ORCA, and so it's a solid second, and that curve here for the program that shall not be named has a certain shape that makes us hopeful that sometime by the end of this year or next year, ORCA will be the most used program in the world. So I think there are a few outstanding features that set ORCA apart, and one of it has lots of high accuracy methods implemented, and that are also very efficient at linear scaling. And I think one of the claim to fame is the DLP and O-coupled clustering method that allows you to do accurate coupled clustering calculations on systems with hundreds of atoms. And then and that is entirely coming from our background as experimental spectroscopists. It's probably one of the most comprehensive packages in terms of calculating molecular spectroscopic properties, and due to the background that we have in magnetism, it also has one of the most comprehensive feature sets for the treatment of magnetism. And one thing that was always very important to me was ease of use, so that it's user friendly. And in fact, when I'm totally self-taught, and there are certain programs that I tried, I could neither compile them nor install them nor run them, and I thought, like, no, it's got to be possible to be simpler than that. But whatever you do, I think that, and that is my closing statement of the scientific part of it, please realize computers don't solve problems, people solve problems, and people, that is you, right? And so the computer program is a really wonderful and powerful tool, but you still have to use it in a diligent and intelligent way, and that is when you solve the problem. The computer itself doesn't solve the problem, right? Mike Zerner, a guy I very deeply admire, he always said the best calculations are those that after I did them I realized I wouldn't have needed them, right? And that is what it means to understand something, right? When you can, like, anticipate the answer that you're getting because you have a picture in your head that helps you understand. Okay, with that,